Alright, last video got to cut off for time, so let's continue in this one. We were working on this last one. We found the initial amount, the amount in 5 years. Now we want to know when will there be 2 grams. So they're giving us the amount. This is the amount that varies, so that's going to go right here in our equation. So we've got 2 equals 100 e to the minus 0.3 t when we put in the amount right there. So it's the same 3 steps every time. The first one is to get e by itself. So we've got 2 over 100 equals e to the minus 0.3t. Next is that we want to do the opposite of what's being done to t. T isn't an exponential, the opposite is logarithm, so you either need to take a natural log or change to natural log. It comes out the same, it's just a matter of preference which one you like to think of. So ln and e cancel, and we're left with ln 2 over 100 equals negative 0.3t, and then our third step is to get t by itself. So we do that, and then we put this in the calculator. Make sure that you have these parentheses like this when you put it in the calculator, and you should get 13.04 approximately, depending on how you round, for your time, and that is in years. Alright, check and make sure your answers make sense. We're starting with 100 grams, and we're going to have less as time goes on. So our initial amount is 100, and then in 5 years we've got 22.3, and then in 13 years we've got 2. So as long as they're going down, generally you're probably pretty okay. Alright, now the last concept for a radioactive material that is important to note is the half-life. So half-life gives us a way to compare various types of radioactive material. It tells us to a certain extent how dangerous they are and what the disposal is going to be like. So if you have something that has a half-life of 5 million years, that means in 5 million years you're going to have half of what you started with. So it's an extremely slow decay. Some things that are created in labs might have a half-life of just a few seconds. So a half-life is a way that we can compare different types of radioactive material. So it's half of what you started with. And it doesn't matter how much you start with. So the half-life is the same whether you start with 100 grams or 1,000 kilograms. The half-life is going to be the same. It's half of what you started with. So let's say for part D, we want to know what is the half-life of this substance. So if we want to find the half-life, that means that we're looking for where it's half of what we started with. We started with 100, so we want to know when our amount is 50. Okay, so that's what the half-life mean is. It's half of what you started with. So you plug that in, and you're going to see it's going to solve the exact same way as the last problem. We're going to get e by itself. And then we're going to take a natural log. And then we're going to get t by itself. If I can squeeze this in here. Alright, and again, you're going to be careful with those parentheses on the calculator. And for this one, you should get 2.3 years. So our half-life is 2.3 years. Okay, so it takes 2.3 to have half of what you started with, and that should, if you look back on our other numbers, that should seem reasonable. Alright, so those 2 examples, we had a growth and we had a decay where the equation was given to us. Let's do one more where the equation's not given to us and we have to set it up. Alright, so let's say that we have a culture that starts with 1,000 bacteria, and in 10 hours we have 6,000 bacteria. And we want to know when will we have 12,000 bacteria? Alright, now this is not linear growth. You can't just figure out how long it takes to get from 1 to 6 and have the same amount from 6 to 12. That's not how exponential growth works. It's going to grow much faster in the next, you're going to have a lot more in the next 10 hours than you did in the first 10 hours. It's going to keep growing faster and faster as it goes. So, what do we know here? We know that we're starting with 1,000 bacteria. That's our A naught. That's going to be our A naught for the entire problem. So we can go ahead and say, or actually let's use P naught for population. Okay, so let's say that that's our P naught. So we're using P of T equals P naught E to the KT. So I know that our initial amount is 1,000, and that number is going to stay there the whole time. Now, the other thing that was given to us in the other problems was the K. This time we're going to have to figure out the K, and we have enough information right here to get K. So if you remember, we've done other problems like this. Plug in what you know to figure out what you need. We know that in 10 hours we have 6,000 bacteria. We should be able to plug that in to get K. So T is 10, and this is our population that changes, the P of T. So if we plug those in, we're going to have population here. 1,000 doesn't move. E to the K times 10. Okay, so we plug in what we know to find K. Now when you look at this, this should look exactly like the time problems. We're just solving for K instead of T. It's a different letter, but it's the same process. Get E by itself. And then you want to do the opposite. The opposite is take a natural log, or change to natural log. So we've got ln of 6,000 over 1,000 equals 10t, and we want to get, k. We want to get k by itself, so we're going to divide by 10 on both sides. And you're going to carefully put this in your calculator, and we're going to get k is 0.18. Now, this is an intermediate step. This is not your answer. You want to keep at least 2 non-zero decimal places for k, so usually at least 2 or 3 decimal places. 2 would be the minimum. It would be better to keep 3. Hopefully in the homework problems they tell you, because otherwise how you round it changes your final answer. Not a big deal for me, but it is for my math lab. Okay, so we got k. That's not our answer. That gives us now our formula. Okay, P of t is equal to 1,000 e to the 0.18t. Now we've got a formula. Now we can answer the question. So the question is, when will we have 12,000 bacteria? So that's now our population that we're looking for. We're looking for P equals 12,000. We're going to put that right here. So 12,000 equals 1,000 e to the 0.18t. And again, we solve. So get e by itself. And then we want to get rid of e, so we're going to do the opposite, which is natural log. Natural log and e cancel. So I'm going to have natural log of 12,000 over 1,000 equals 0.18t, and then we get t by itself. Okay, so we're going to put all that in the calculator super carefully, and we're going to get 13.8. Okay, 13.8 is equal to t. Come back to your problem. Our unit is in hours. Okay, 13.8 hours, and then double check to make sure that that makes sense. We started with 1,000. In 10 hours, we had 6,000. And in 13.8 hours, we had 12,000. Okay, that seems reasonable. Sorry. It's going to go up as The time goes up, and it's not going to be linear, so you're not going to be able to estimate it, but as long as the numbers are going up, then that's a good answer.